mainly on computer vision projects. We try to find problems within Africa that can be solved with artificial intelligence. And then we try to basically build solutions to this problem. So we are basically focused on impact-driven research. Okay, so yes, so I'm presenting today on machine learning models for classification, and before that, I want to do like some throwback. So this is the first IndabaX in 2019. It was at the Kofi Annan ICT Center, and then this is me there. And I mean, it was a great time there, and I'm happy that I'm here again today, and I'm also seeing many of the faces that I saw there. So Clifford is somewhere here, Clifford is here. I can see many. Delali is also here, many of the other faces, and it's great to be back. Yeah, Delali was kind of shouted off. Okay, so today we are going to be talking about machine learning models for classification. But Abigail has already spoken quite a lot about machine learning. She did mention supervised learning. And so when we talk about supervised learning, it's mainly the most common form of machine learning out there. Most machine learning would be in this domain. And so when we talk about supervised learning, we have some features, right? So we have some features of our domain, the problem domain that we can measure. And then we have some response Y. So we have some data vector X, and then some response Y. And then we believe that given X, we should be able to predict Y, right? So we think that there's a relationship between X and Y. And so when we are doing supervised learning, we are just dealing with the set of approaches for estimating this function F that relates our X and our Y. Because we don't have the true relationship, we don't have the true functional relationship between them, we are trying to estimate that function. So that's all about supervised learning. We are trying to find this function, and then we are thinking about different approaches for estimating this function F. Right. So we have some input data. These are the response or the targets, and then we build a model to relate these two together. Right. And then typically with supervised learning, there are two broad categories of problems or tasks that we have. So there's regression, there's classification. When we talk about regression, we are trying to predict a continuous value. So the target is a continuous value, right? So remember I said we have a data feature X and some response Y. When we are doing regression, the target is continuous. So a typical question will be what's the temperature tomorrow? It could be 84.1. It could be 84.123. Like it's continuous. There's an unlimited range of values that we could predict. And then when we talk about classification, we are trying to predict a discrete category or a discrete categorical value. So the same kind of problem dealing with the weather, but here we're asking, is it hot or cold tomorrow? So we have two categories that we are trying to predict. And so today we are going to be dwelling on classification. So the classification problem deals with the understanding of a data set of a problem domain, trying to recognize groups within that data set, and then trying to recognize those groups. So here we have a data set, and we can see that we have three distinct blobs. So we have this blue, this green, and then this orange blob. And when we are doing classification, what we're essentially trying to do is to find some boundaries between those classes. So we are trying to find something that will be able to create a boundary between these classes, such that when we have some new data, we can now know, okay, is this new data part of this class, or the other class? So it's all about trying to find these boundaries that would separate our data set into the number of classes that we have, or the number of categories that we have. And then so classification is widespread. It's applicable in a lot of settings. One such application one project that we we worked on some time ago was for cocoa disease detection. So we can take pictures of cocoa pods, a part of the plant, and then the idea here is to detect diseases. So can we, given the cocoa pods, can we detect is this diseased? I'm only listing black pod here, but then as you would know, there are many other diseases that we could have. And then we try to predict the diseases or detect whether it's a healthy pod. Right? So that's a distinct category, the number of diseases that we have. And then Abigail already mentioned this. It's a project that we work on here in the research team here in Accra. What we try to do is to take these high resolution satellite imagery and then try to do classification per pixel. So the previous slide, we are doing classification on the image level. The whole image, we try to see, okay, is the cocoa pod in the healthy, black pod, swollen shoot, whatever. But then here, we are trying to do classification per pixel. So we are not doing classification on the whole image, but then take every single pixel in the image, and then we are trying to recognize what is that. So for instance, is that pixel a building? Is it part of a road? Is it whatever it is, right? So typically we are looking for buildings and we are looking for roads. So that's per pixel classification. So the data, the problem is different, but then the setting is the same. We are trying to identify categories, right? And then as you would see, that's how it works in maps, in Google Maps. We take these high resolution satellite images, build models to identify buildings, identify roads, and then we can ingest that into Google Maps, right? And then we could have sound. So we can have sound, and then we try to classify, is it an earthquake? Is it an explosion? We could even have more categories. Is it vehicles? Is it human sound and all of that? So that's also an application of that. So this here, we are no longer dealing with images. We are dealing here with audio. And then we could also have text. So we could do sentiment analysis on text, right? So what I did was to basically pull some tweets on e-levy. And what we could do is that we can build a model given this corpus of text. Can the model tell us what is the public sentiment on the e-levy, right? So here we can see someone says e-levy is the worst tax policy in the history. Clearly a negative sentiment, right? But then somebody else says if the e-levy is so far not bringing in the estimated revenues, it does not mean it is a bad task. A bad task. The person is clearly in support of the e-levy, right? So here we are trying to detect from a text, is it a positive sentiment or a negative sentiment? And this could be a nice thing to do. Can we pull tweets and then detect or learn about the sentiment of the Ghanaian public on issues that's affecting the populace? So this one nice application of that. And then maybe as an aside, maybe you can try to classify or predict who said it's not a bad task. And then maybe you can see me after and let me know who you think it was. So what kind of data do we need to do classification when we are trying to build machine learning models for classification? Like I've said, I already mentioned for supervised learning, we have some data X, which contains some features. So now these features are individual properties of our data domain, individual properties that we can measure, right? So here we have a data set for shapes, and then we are measuring the length, the width, and then the mean speed over ground. And then these are the features we are measuring. So these features are it's our X. It's what we think is related to our Y. And then the Y here is the type of shape we are dealing with. So we have these features and we want to relate that with the shape type. So given the length, the width, the speed over ground, can we predict what type of shape we are dealing with? So when we take all of the features together, we have a feature vector, all of that together, feature vector, and then we have a category, the passenger vessel or sailing craft or any other type of ship. And then when we combine the feature vector together with the category or the label that we have, we call that an instance. So if you look at this, it's one row in our data set, and it's one shape. So we go to the hub, we take one shape, we measure these properties, then we label it. That is one instance. Then we could do the same thing for multiple shapes. Then we have another instance. So all of that one row is a single instance in our data set, right? So if when we are doing classification, we need these features, and then we need a label, right, together to get an instance. But then, like you could have inferred from all of the examples I've given, the data can come in different forms. It's not always coming in as images or as coming in a tabular form. You can have it in different forms. But then the important thing is that to do classification, every feature vector is associated with a class label. So if it's text, you still have a label. It's audio, there's still a label, right? Okay. So when we are trying to do classification, there are different ways the problem might be framed. The one common one is binary classification, where we are trying to identify two classes. So we have, in this example, cats versus dogs. So we have pictures of cats, pictures of dogs, and we are trying to build a model to just identify, is it a cat or a dog, right? So it's a binary two-class problem. And then you may know that we cannot feed, for example, the word cat directly to a model, right? Computers do with numbers. So we may turn cats and dog into numbers. So we might call this class 1, class 0. Depending on the number of classes that we have, we translate that into a numerical scale. Now that doesn't mean if a class is class 5, that is like a higher class than class 0. But then it's just to help us to build models for the problem. And then there's multi-class classification. So here we have multiple classes. You can have cat, dog, truck, whatever you have. And still the goal is to predict a single value or a single class. So in all of these single binary classification, multi-class classification together, we call them single label problems. That is, we are trying to predict a single label. But then we could have multi-label classification. So here, the whole with single label problems, every image is associated with exactly one label. When we are doing multi-label, one image can be associated with multiple labels. So here we have like a dog, a cat, a donkey. So if our model sees this image, it has to tell us this image contains both a cat, a dog, a donkey, and what have you. So that's a multi-label classification problem. Okay, so now that's an overview of classification. Now, how do you build models for these classification problems? So generally, when we talk about supervised learning of models for supervised learning, there are two broad categories of models, two broad families of models. So we have models that are parametric and those that are non-parametric, right? So going back to what I mentioned about supervised learning, the whole idea is to estimate a function that relates our x's and our y's. And so what differentiates parametric and non-parametric models is in how they model that function. So when we talk about parametric methods, they reduce the problem of estimating that relationship between x and y to one of a finite set of parameters. That is to say, these parametric models make an explicit assumption about the form of the relationship between our x and our y. So for instance, we may build a model that assumes a quadratic relationship between x and y. And we know a quadratic equation, ax squared plus bx plus c. So it fixes the form of the model and it reduces it for us. So it kind of simplifies the problem space. And now all that we need to figure out is what is the A, what is the B, what is the C. Right? If our model assumes a linear relationship between x and y, then we know like an equation of a line, y equal to mx plus c. Then all that we need to figure out is what is the slope m, what is the intercept c. Right? So those are parametric models. And then there are many examples of that: logistic regression, support vector machines. And then the non-parametric models don't make any explicit assumption, right, about the functional form. So for the non-parametric models, the functional form can change depending on the data. So any data set I give to it it kind of it morphs to fit the particular data set that you have. And because of that, the complexity of a non-parametric model grows with the data set, right? The more data you give to it, the more it has to grow to accommodate the data. And then there are other examples of the k-nearest neighbors and decision trees. So for the purposes of today's talk, I'm going to be focusing on logistic regression. One, because I feel like I think it's one of the simplest, and then it's easy to generalize from logistic regression to neural networks, which are making a lot of waves these days. So when we are building a logistic regression model, like remember I said, parametric methods are making an explicit assumption about the functional form between X and Y. So parametric logistic regression assumes a linear relationship between X and Y. Right? Now, a typical problem that is we can draw a straight line to divide between them. So this problem is one that logistic regression can deal with easily. Right? So we assume a linear relationship. We fit an equation of a line y equal to wx plus b. W is our slope, b is our intercept. And then what you try to do is to model the probability of our y belonging to any of those classes. So logistic regression is for binary classification problems where we have two classes. And then we are trying to model the probability that our y given our x belongs to either class 1 or class 0. Right? So instead of building a model that predicts that, okay, given x, this is part of class 1, this is part of class 0, we are rather trying to predict the probability. This example, we can say with probability 0.8 that it's part of class 1. Right? So we are trying to model that probability. So like I said, logistic regression makes a linear assumption. So we first fit the equation of a line. We figure out this W and this B parameters. And then we have this line here. But then we are trying to model the probability of belonging to one class or the other. But then, and then if we have a line, we know that a line is continuous. It can go in the negative direction, and we can have large negative numbers. We can have huge positive numbers. But we are trying to estimate a probability, and we know that probability falls between 0 and 1. So we need to find a way to take these continuous values that our linear equation here gives us and transform that into a value between 0 and 1. Right? So we do that with what is called an activation function. And for logistic regression, the activation function is the sigmoid function here. What it does is that given any number, it returns a value between 0 and 1. And we take that as a probability. Right? So we give this value here to it, and then it returns a probability to us. And this is the probability that our example, our X here, belongs to class 1. Right? So we are predicting probability of Y belonging to the class 1 given our X. Now, when you have that probability, we need to decide on a threshold. So the probability is between 0 and 1. Now, if an example has a probability of 0.9, is it part of the positive class or not? If an example has a probability of 0.6, is it a member of the positive class or not? So to make that decision, we typically decide on a threshold. And it's common to use a threshold of 0.5. So if the probability is greater than 0.5, we say, okay, it's part of the positive class. If it's less than 0.5, we say it's part of the negative class. Now, the main problem now reduces to finding these W and B parameters, right? That's all logistic regression is about, trying to figure out the best W and the best B, the best weights and biases of our model. The best weights and biases of our model. So given our data, what we try to do is, okay, given X and an associated class, X and a Y, can we find W's and B's that make our model predict the class as closely as possible, as best as possible, right? So if this X value this you have a particular example that's part of the positive class, then we want our y here, our probability here, to be as close to 1 as possible, right? And then if you have an x that is part of the negative class, that is the other class, then we want this probability here to be as close to 0 as possible, right? So because they are two mutually exclusive classes, and so if it's not part of A, it's part of B, right? And then we know that probability would sum to 1. So if y here is the probability that belongs to 1, it belongs to the class 1, then the probability of belonging to the other class is 1 minus the probability of belonging to the other, right? So we want to push for the negative classes to push it as close to 0 as possible. And for the positive classes, we want to push the probability as close to 1 as possible. And then we do that with a method it's called maximum likelihood, right? I'm not going too much into details of that. This formula here might seem like a big deal, but it's not so much. So essentially, what we are trying to do here is that for the positive examples, so for all the examples that are coming from the positive class, we want to maximize this probability, make it as close to 1 as possible. This is the product, right? And so we are multiplying numbers, probabilities. If you are multiplying numbers that are close to 0, at the end we have a smaller number. If you are multiplying numbers that are large, at the end we have a large number. And so we are trying to do that for the positive classes, push probability as close to 1 as possible. And then for the negative classes, push probability as close to 0 as possible. And we call that maximizing the likelihood, right? Now, in practice, we don't maximize the exact formulation that I have here. This is the basics of it. But then in practice, we maximize the log likelihood, because log products are difficult to deal with. If you are multiplying very small numbers, it becomes smaller and smaller and smaller and smaller and smaller. And computers can't deal with very small floating point numbers. If the floating points, the decimal points become huge, computers reach their limits, right? But then if you take the log of a product, we get a sum, right? And then if you translate that into a sum, sums are easy to deal with. So in practice, we maximize the log of this, but it's still the same likelihood function. Okay. So that's how we build a logistic regression model. And like I mentioned, this is for multi-class, binary classification. That's the logistic regression model. But we can generalize this to a multi-class problem, right? And then generalizing it to a multi-class problem gives us an easier way to even extend that to a neural network, right? So this is the same binary logistic regression model that I had, just drawn in a different way. So here we have our inputs here, and then the lines that are coming in is where we have our WX. So our weights are now on these lines. And so each line is doing this WX, and then we sum everything here. So WX plus B. We have this here, it's like a summation of all of these inputs or features that we have. And then we have our activation function here. So this is the same logistic regression model that we have. But then with this formulation, we can easily move on to a multi-class problem. What we do is that we have one output node. We call these nodes. To move from a single a binary classification problem to a multi-class classification problem, we add more output nodes. So we move here, and then we have more output nodes. So here it's like n number of classes. So the number of nodes here are the number of classes that we have, right? And each one of these is still doing exactly the same thing that we have here. So nothing has changed. It's still the same calculation that we have here, but we are doing it n times, where n is our number of classes or the number of categories we have in our data set, right? So it's the same thing. It's like doing a binary classification or binary logistic regression n times for our n classes with a different set of weights. And now when we have these n numbers here, we still need to produce a probability, right? But then here, because it's multi-class and a single label, we want to predict a single label for our input. So we change the activation function. So previously, the activation function was a sigmoid. When we are dealing with multi-class problems, we have a softmax. which takes all of these and gives us probabilities that sum to 1, right? So it takes these 4 numbers and then assigns probabilities to each one of them, such that when you sum the probabilities, so you would get 1. And then the maximum of these numbers would be the class we want to predict. So if you give it an example and gives, say, 0.6 to this class, 0.2, 0.1, 0.1, then we take the maximum of that, which is this 0.6. So we predict this class as our label. Now, the next step beyond this is that we can take this same thing and now move onto a neural network, right? So when you talk about neural networks, they are simply multiple logistic regression models stuck together, right? So we have a multi-class logistic regression model here. And then instead of taking this output as the final output, we stack another multi-class logistic regression model on top of it. Then we stack another. So the deeper we go, we say we are doing deep learning, right? So we just stack more and more on it. And now we have a deep neural network. So here, up to this point, it's a multi-class logistic regression model. We add another layer, right? And then we build a neural network. So essentially, a logistic regression model is a single layer neural network, right? Okay. And because we are now doing this stacking of layers, this neural network can do complex stuff, right? Because the logistic regression model here just takes this linear, draws a linear boundary on our data sets. But then a neural network takes these ones and then computes complex features based on the features of the previous layer. And then it does that a number of times. Because of that, it's able to approximate more complex functions. Right? So for instance, this data set that I show here is clearly not linear. We cannot draw a straight line to separate these data sets. We have some of the classes here, some of the classes there. The blue classes too are dispersed this way. So we cannot draw a straight line to separate this data set. But then when we build a neural network, it can now draw something that looks more complex than a linear plane, right? So that's the benefit of neural networks, is that as we go deeper, we can approximate more complex functions. Now, if we have a model, how do we evaluate how well our model is doing? And that is the whole aim of machine learning. If you have a model that does well and you can't evaluate it, you can't give a measure of how well it's doing, then the process wouldn't have been useful, right? So we need to be able to evaluate how well our models are doing. So we say that a classifier is good only if it provides accurate predictions on unseen data. Right. Now, if you build a model and it does well on the data used to train it, well, it's good, but then is it of much use in the real world? So to find out whether a model is useful in the real world, we need to be able to test it on data it wasn't trained on, right? And so to kind of approximate that, when you are training a model, we typically would divide our data into a training set and a test set. So the test set is not used to train our model. We only train on the training set and then fit our model, whatever model we train on the training set. When we are done, we evaluate on the test set. So if there was a golden rule of machine learning, it would be that you never use your test set to train your model, right? That's the golden rule. Never use your test set to train your model, because it's supposed to give you an estimate of the generalizability of your model. How well would it perform in the real world? So how do you evaluate our model? One common measure is accuracy to evaluate a classifier. So accuracy is the total number of correct predictions our model makes over the total number of predictions. So if you give it 100 examples and it predicts the correct label 90% of the time, then our model is 90% accurate, right? Now, accuracy is kind of like the default metric out there, but then it's not the best in many situations. The main problem with accuracy is that it treats all examples in the same way, right? Now, let's look at that with this example. So this is a data set where the company is trying to detect fraudulent activities on their website from the mouse movement of users. So they try to capture how users behave on their system, and then they try to predict fraudulent behavior from that. And if you have ever built any fraud detection system, you know that the positive classes are rare. So many of your users will be legitimate users. The real fraudulent activities are very small, right? So you may have, say, 99% of the time being normal users, and then 1% being a fraudulent activity, right? And so if our model just predicts that everybody is a legitimate user, that model will be 99% accurate, but it will really be useless. We cannot use it anywhere, right? And so accuracy wouldn't really give us that information, right? And so we need like something else than accuracy. So the takeaway is that you need to know more about your model than what accuracy provides for you. So this confusion matrix that we have here is not a metric, but then what it does is that it gives us deeper insights into the predictions of our model. Right? It breaks up accuracy into these 4 categories. So the true positives are cases where our model says that this example is a positive class, and then that's actually the right thing. And then true negatives, it says that this example is a negative example, and then that was actually the right thing. So that's when our model is doing well. And then false positives are when our model predicts that this example is coming from the positive class, but then it's actually from the negative class. False positives are referred to as type 1 errors. And then false negatives are when our model predicts that an example is from the negative class, but then it's actually a positive example. And those are referred to as type 2 errors. So now, based on these confusion metrics, we can now come up with other metrics, which are more informative. So one such metric is the precision. So precision tells us how good our model is at predicting, how good our model is when it predicts the positive class. So when our model predicts that this example is a positive example, how confident are we that the model is right? Right. So essentially, it tells us that when our model says that this example is positive, what's the fraction of times that it's correct? And then recall also measures how good our model is at correctly predicting the positive class. Right. And so when our model says that this example is positive, precision is telling us how much do we believe in that prediction? And recall is telling us that for the positive class that we care about, how well is our model doing on it? Right. Now, typically, precision and recall are in tension, because if you are building a model, if you try to increase precision, recall would reduce. If you try to optimize for recall, precision would reduce. And so what you do is that for the problem at hand, you need to determine which of these is important for you, right? And so for some problems, precision might be the best thing to go for. For other problems, recall might be the best thing to go for. So for an example, if you are building a model to classify spam and emails into spam or not spam, precision here would measure that if our model classifies an example as being spam, right, and then puts that into the spam box, that if that example turns out to be not spam, what that would mean is that our user would have missed out on some important email, right? And which is bad. We don't want our model to make those errors. False negatives here for the recall would be that our model wrongly misses a spam email. So there's an email that comes in that spam, and our model is not able to detect it, and it comes into your inbox. Now, if you look at those two types of errors, your user would be okay with seeing spam once in a while than getting an important email going to the spam box, right? And so for that problem, you would want to maximize precision, right? So the problem will determine which of these metrics you want to optimize for. And then we have the F1 score, which is a harmonic mean of precision and recall. It's basically a single number that we can use to evaluate our model. Okay, so if you build a model, another thing that we normally think about is the generalizability of the model. As I've spoken about, we want to see how well it will do on an unseen data, right? And then when we typically try to evaluate these things, one issue that usually comes up is whether a model is overfitting or underfitting, right? So these are concepts or things that you would see. So when you talk about underfitting is when our model is too simple for the data set that we have. So we have here data set that is not linearly separable, and we are trying to fit a logistic regression model to it. Right. So our model, it won't do well on the training sets, and as such, it can't do well on the test sets. When you talk about overfitting, it's when our model is too complex for the data set that we have. Right. So here we fit a high degree polynomial, and then the model tries to pick out everything. And what it ends up doing is that it picks up both the detail and the noise, right? Because there's measurement noise when we're trying to gather data. And then when a model overfits, it picks up the noise too as detail. And what that means is that if you take this model and evaluate it on a test set, it would fail because it's no longer learning important detail, but it's learning noise in the data set. What we want is somewhere in something in between. So we don't want a bad model, a model that's underfitting, but I don't want a model that's too good on our training set, right? We want a model that does well on the test set. So the test set is our measure. It's what we are looking for, right? We don't use the training set to evaluate how well our model is doing. So to kind of make this even more practical, I spoke to some of the engineers, the researchers on our team, trying to ask them, can they give examples of practical instances where they faced an overfitting problem? So I got this example from one of our researchers. So they were working on a problem where they would try to identify nodules in chest X-rays. So nodules are things that signify cancer. Maybe cancer is probably developing in the X-ray in the chest area. So they got lots of these examples. Some of them were very old. Now, the problem was that some of the data that they had, some of the doctors had drawn markers around the nodules that they suspected to be cancer, and they didn't know it, right? So when they suspected something to be a cancerous image, they would draw some markers around it. And they took those images and they used it to train a model, right? And that is noise. That's not what we really want the model to learn. We want it to learn what actually makes a nodule cancerous or not. But then because those red markers were there, the model actually learned those features, right? It didn't learn what actually differentiates cancer from not cancer, but then picks up those red nodules that are just noise, those red markers that are just noise, right? And then in the end, if you take that model and you put it in the real world where those red markers are not there, the model fails, right? Okay, so this is where we want what we want. We want something that is somewhere here, something that is in between. So when we start training our model, if you are using a simpler model, both training and test error are high. As we go down, training and test error reduce, but at some point they diverge. So when the complexity of the model increases, our model, the training error goes down, but then at some point the test error begins to go up because then the model has started overfitting. So you want the point here. And if you are going to use our test set to do this evaluation, then at some point the test set no longer is independent because we are kind of using information from the test set to determine the best optimal solution. The goal of a test set is that we want it to be an independent evaluation of the performance of our model. So for this purposes to detect overfitting, we would typically divide our data sets into a training set, a validation set, and a test set. And then we use the validation set for this purpose, and then the test set still becomes an independent evaluation of our model. So how do we avoid overfitting? So to prevent overfitting, one thing to do is to reduce the complexity of the model. So if you are fitting a quadratic, can we do like a linear model, right? And then another thing is we use what we call regularization. So when we do regularization, we try to force the model to learn simpler weights or smaller weights. So it's kind of trying to reduce the complexity of the model, but then we don't touch the model form itself, i.e. we can maintain a quadratic functional form, but then we put a constraint on the model such that the weights cannot grow out of bounds, right? And then if you have done regularization, there are many other forms of regularization as well. So in computer vision, we have what we call data augmentation. We have early stopping. We have many other techniques for combating overfitting. But then if everything else fails, then you may need to get more data, right? Because if you have like a few examples, then it's hard for your model to not overfit on that data set. And then to avoid underfitting, what you do is to increase the complexity of a model. Or if you're already using regularization, can you reduce regularization? Right. Okay, so I wanted to, before we talk about a few open problems, just talk about one example here. So a common thing that you might hear when you look at the bars and then all of these new stuff, diffusion models, DALI, and all of that, it's as if artificial general intelligence is already here, right? We have robots that can do everything that we want them to do, but then there are more open problems that are there to solve. So we've talked about classification today. One open problem that is still difficult to do is few shot learning. So what we've spoken about, even for overfitting, I said you try to get more data, right? But then when you think about it, humans are able to learn with small data. So for instance, if you have never seen an orange before, right? And then, or maybe let me even give you a more practical example. So at the office, we have, in our team, we have people from many other parts of Ghana. And then there are some parts of Ghana where they don't have something like plantain. Part of Africa where they don't have something like plantain, right? And so I was talking to some of our people, our colleagues, and then they were like, they don't have plantain in their country. They only have banana. Now, they don't need to see 1,000 examples of plantain to be able to identify plantain the next time they see plantain. Giving just one or two examples, the next time they know that this is plantain, right? But then computers can do that. We need lots and lots of training data to be able to identify, learn what the good features about a data set, right? And so few shot learning is where we try to classify a data set with a few examples. So giving 2 examples of a class, can we build a model that is able to identify all any other examples from that problem domain? And this is a very much open problem that is still open for solutions, right? So if you are thinking of research problems or anything that you want to consider in this space, it might be a good thing to consider few shot learning or any other problems like this that have not been solved. Okay, so that's it for today. Thank you for your time.
Thank you very much, Emmanuel. Please, it's time for questions.
All right. Good afternoon. Thank you for your presentation. So in avoiding overfitting, you made mention of getting more data. Okay, so in a case where the only place I can get data is from public offices, public places, and then you know that those places, obtaining data from those places is very, very, difficult. And then I try and then reduce the model's how do you call it, complexity. Yet I'm not getting the expected feedback. How do I go about it?
So I didn't go much to regularize, but then so for instance, if you are building a model like a computer vision model, before you even decide to go for more data, there are many other things you could try, right? So one example, I spoke about the Cocoa thing. So the first model that we built for the Cocoa was just on images that we scraped from the net, like the internet, and just a very small data set, right? But then in computer vision, what we can do is we do transfer learning. That is, if you train a model on a very large data set. So in computer vision, there are standard large data sets of 1 million images, 300 billion images. So what we do is that we train on these data sets, and then of course they're not exactly what you want, but then they give you a good starting point, right? So we take those models and then we transfer it into our domain, right? And then we see how well we can do with that. And so typically, if you do transfer learning, it gives you a huge boost in performance than if you have not done it, right? So what that basically gives you is that it gives you a way to start off based on somebody else's knowledge. We can put it that way, and then build up on top of that. So there are many other ways before you got to the point of needing to get more data that you can explore before you reach the point where you can say, okay, all of these things have failed, and then the only way out is to get more data.
All right, thank you for your presentation. So a quick follow-up question to what he asked. In getting more data, it's kind of suggests that it will take you back to the stages where you're supposed to make sure that your data is clean before you actually start building your model. So how do you ensure that you try to minimize the time that you spend in getting your data clean before? Because from what you are saying, it's like you are in the process of working with your model, but you realize, okay, you have to go back and get more data. So how do you ensure that once you have that data, you don't spend so much time trying to get it clean and make it ready for the model before you continue your work?
Well, so when it comes to making your data clean, there's really no way around it. Your data must be clean, right? And so depending on the problem, some problems, it's very difficult to get clean data, or not even clean data. You can get the data, but it's difficult to label, right? So for instance, I mentioned this pixel classification problem. It's a semantic segmentation problem. You are labeling every pixel in the image, right? And then somebody who is labeling could spend as much as 90 minutes on a single image, right? 90 minutes. So that's like more than an hour on a single image, right? And then if you want a data set of, say, 100,000 images, like you can multiply that by 90 minutes. So when it comes to getting clean data, there's really no way around it. You have to get clean data. But what we can do is that, so for instance, on that project, because we already have some labeled data, when we are going in for new data, what we could do is that instead of giving those images for the annotators to start from scratch, we could use the models you have already built, although they are not perfect, but then it kind of gives them a start. So the model gives some predictions, and then the annotator, all he has to do is to kind of correct what the model has done, right? So it kind of reduces the time spent in labeling, right? So you could use what you have done to kind of help the annotator do a better job.
Question is during the training and testing and validation of the model, how do you select the data sets? Would they go through another feature selection, or are they selected randomly? And what are the criteria? Maybe 70% of the data will be for training, 20% will be for testing, or 10% will be for validation. How is the process being done?
So for the way you select the examples typically depends on the domain. So for instance, in computer vision, you are dealing with images, we typically would pick random samples, right? But then if you are working on a problem that deals with forecasting, where you are trying to forecast maybe sales or something, you cannot pick random samples, because if you pick random samples, so for instance, if you pick today, right, and then your model already sees yesterday and sees tomorrow, it's easy for it to predict today, right? Because it can just interpolate, and then because there may not be a sharp drop from yesterday to today, right? So the domain will determine how you pick your data. So for an example like forecasting, you might pick the next 6 months, right? And then that would be like your test set, and your model tries to predict that, right? So the domain will determine that. And then as to the percentages, so for instance, in computer vision, it's typical to do, say, 70, 10, 20, right? So you have 70 for training, you have 10, and then you have 20, right? Some will do 80-20. There are no hard fixed rules for that, right? And then I didn't mention it, but then there are cases where your data is not enough, and then dividing it and holding out 30% of it, you can't afford that, right? So there are methods where you can train. We call them holdout validation. So you train on say 90% of it, evaluate on 10, and then you do that 10 times. So each time you train 10 different models, each of them train on a different subset. And then at the end of the day, you can kind of average over the whole, all of those 10 models, and then find how well your model will do, right?
Yes. So my question is, so with most of these classification models, you will split your data sets into your training, testing, validation. But mostly when we do feature extraction and then the standardization and the normalization that we do it on the training data set. And so when we are testing it on a model, I don't know, do you have to still do the normalization on the training data set? And also when you are deploying your model with the model, should every data set or every sample that's tested on the data in real world go through that process of normalization and standardization before it predicts?
Yeah, so what you do is that the same normalization process is applied to your test data. So for instance, when we are dealing with images, one thing is to do like mean subtraction, subtract mean, divide by standard deviation, and then we may do it per the data set. So we will take the mean of all of the data, right, and then take the standard deviation. So that's like your data set statistics. That same statistics is what you use for your test set, right? So you don't go in and then take the statistics of your test set, because you are trying to, in real world, you're not getting a bunch of images at a time. You are getting maybe one, right? So we are assuming that the statistic that we have is kind of like a good estimate of the mean and standard deviation of the whole population, right?
So there's a question online, and I read, if I want to use the crying of babies to predict whether or not they are sick, hungry, or just want their mother, how can I use classification to solve this issue?
So if I get it right, you want to use the crying of a baby to predict whether the first thing I can think of is, how would you label such data? How would you ask the baby, are you hungry? Because if the baby is hungry, he would have already said it, right? So like I said, you need to be able to build a classification model. You need features and you need labels, right? So if you can label it, that's fine. So what I've seen something that an application that deals with babies, where you are trying to detect like early signs of some diseases, right? So for that case, I think medical doctors can do that, depending on like there are some things they look out for, and then they use the cry of the baby to predict this baby is probably suffering from this particular disease. So you need somebody who can label that data. So if there's somebody who is really an expert with babies and knows that if the baby cries this particular way, it means that the baby is hungry, then that person labels your data for you, and then you can build a model.
Okay, so I have another question. This has been on my mind for a very long time now. It's due to the facial recognition on my phone, especially with the Apple products. With the issue of COVID, when you wear a nose mask and you put on your phone, the facial recognition doesn't work because it needs to work on all the face. So I was thinking if it's possible for the facial recognition to really pick perhaps your forehead, the cells on your forehead, because you made mention of the multi-class neural networks. When another class is being joined to another class to really have a deep learning platform. So I was thinking, is it really possible for that to work? But I was thinking maybe with the issue of the Apple releasing a new software, I thought maybe they will actually put that into practice because of the COVID and all. I
mean, I've not worked on facial recognition before, but if they are not doing it, then it would mean that probably just this part is not enough, right? So like if you are doing facial recognition, there are some things that your model should be able to learn, right? And so maybe you need the whole face to be able to get all the sets that you need to be able to rightly differentiate between people, right? But then it's not a hard problem to do from the way you have framed it, building a model to predict people with mask on, right? When COVID came in, I saw some things online. People built models to detect mask on, mask off, these kind of models in relation to COVID. So it's easy to be done, right? But then the thing is, will it work well in practice, right? Because facial recognition is a difficult problem, right? You need to be able to make sure that nobody can fool that algorithm.
Okay, so I want to find out, with your level of experience in terms of image classification, which of the algorithms is your go-to algorithm when you want to quickly do a deployment?
Sorry, I didn't get the question.
Which of the algorithms, when it comes to classification, it's your go-to algorithm when you want to quickly do a deployment?
Okay, so these days, ArrestNet is like a standard computer vision model for classification, right? So typically, I would start with ArrestNet, right? And then you can go on beyond there, but residual networks have kind of become very, very widespread within computer vision. So it's kind of like a baseline that we compare many other models against, right? So it's in many cases, ArrestNet is like the baseline, and then you try to build on top of it, right?
So there's a question online. Thank you very much for the deep and meaningful presentation. Since we are in an African context, according to you, how can we as young graduates or researchers be able to learn, work and apply AI in our contextual data sets? What will be the path for customizing AI for Africans in education and industry?
Can you read it again? I want to get it.
So, according to you, how can we as young graduates or researchers be able to learn, work and apply AI in our contextual data sets? What will be the path for customizing AI for Africans in education and industry?
Okay, so I think the premise of the problem is the question is it's splendid. I mean, and I think that should be something that all of us should be looking at. We should be looking at moving beyond building like general stuff like image classification models on data sets out there, which are not really contextual. They are not really solving problems within our space, right? We should be looking at, it's still the same image classification, but trying to solve problems within our own context, right? So for example, I mentioned the cocoa problem. It comes the ideas or the inspiration, if you call it that way, comes really from talking to people, right? So typically what happens is that you are the one who has the skill, you can build the models, but then you don't have the problem that you want to solve with it, right? And you can only get problems if you talk to people. So for instance, one example was I worked on a project, even this cocoa project that we did, the idea wasn't from me, right? It was another member of the team who had that idea, and then we built it, right? We formed the team, we built it. Another thing that I worked on some time ago was, so my undergrad was in the University of Mines, and it's like in a mining community. Mining is big, and in UMA too, there are a lot of people who manage mining-related courses. And then around that time, I was thinking of problems that I could solve release things that I was building. And then I remember I was talking to a friend of mine. He saw me building, I think it was an image classification model or something. And then he is a geologist. And then when he came in, he saw it and was like, oh, can you build something to identify minerals? Right? He was a geologist. He saw that and immediately thought about something for his field. Right? And then that became my final thesis and eventually became a paper. Right? So that's how you get problems. You talk to people in people, you talk to people, and then get ideas, and then build teams with people. You can't really, if you are really looking to solve societal problems, you can't do that alone, right? So build teams of people who can work together towards solving some of these problems.
Okay, thank you very much, Emmanuel. So we are done with the first part of today's session. So we're going on a lunch break. So the protocol team will lead you to the lunch area and then we can have lunch. Thank you very much.